So before we begin, this is going to play into what we're doing today. I would like you to, given the function f of x equals 3x plus 2, I would like you to algebraically find the inverse, and then right next to it, graph the function 3x plus 2 and the inverse in the same coordinate plane. All right? What type of a function is f of x equals 3x plus 2? What type of it? Is it linear, quadratic, exponential? What is it? It's linear, so it definitely has an inverse, okay? Right now in your table groups, go ahead and do that. Let me through this. So hopefully you remembered how to algebraically solve for the inverse of a function. What's the first thing we do? Yes. Good. So we say y is equal to 3x plus 2. Then we switch the x and the y. So x is equal to 3y plus 2. Then we subtract and we resolve this thing for y. So I'm going to get x minus 2 all divided by 3 gives me the y. So that means that f inverse of x is equal to x minus 2 over 3. Is that what you guys got as well? Yeah. Good. And then over here I asked you to graph it, which I'm going to do right now. Bam. Check that out. Okay. So the red graph represents f of x, which is the 3x plus 2, right? And then the blue graph represents f inverse of x, which we found over here to be x minus 2 over 3. What does the green graph here represent?
It's just the axis y equals x.
Yeah, the line y equals x. And notice that the red and the blue, right, the function and its inverse are reflected over that line y equals x. Okay? So what can you say then about this point here? What is this point? 0, 2. Okay? So if 0, 2 is on the graph of my function, what point is guaranteed to be on the graph of my inverse then? Yeah, we just switch the x and y, right? So notice the point. There it is. Right there, 2, 0 is on there. Now, is that true for every single point on my original function graph? Yes, it is. It's very, very true. Okay, good. This is going to play a role into what we do next, okay? So here's what we're going to do next in part 2. I'm going to ask you to do the exact same thing, except I'm going to give you a function, f of x equals 3 to the x. Now, this is no longer a linear function, right? Instead, it's what type of a function? Exponential. Amy, nice job. This is an exponential function. Good. I would like you to find, okay, f inverse of x and graph both, okay, using the same principles that we just talked about up above. So over here, give me the algebra. Over here, give me, there's an A in that, give me the graph, okay? All right, so today is the day that we find out how we get ourselves out of this situation. So here's what we know so far. So applying the same rules, we would say, okay, y is equal to 3 to the x. You guys got that far. Then you'd set x is equal to 3 to the y. Whoops. Yikes. 3 to the y. And then how do you solve this for y?
Oh, you bring like the y root of it.
Yeah, we could take everybody always says take the y root of it, okay? So if I take the y root and the y root, so I get the y root of x is equal to 3. Have I solved that for y?
Yeah.
No, so I have? No, I haven't. Okay, that's no good. So that's not going to work. Okay, so, sorry. So that means I still have y equals 3 to the x. So x equals 3 to the y. How do I resolve this thing for y? We are stuck, right? We are stuck. So let's abandon that for 1 second, okay? And let's go to the graphical representation. Grant? Let's go to the graphical representation. So let's go back to this function here. This is an exponential function, correct? There are 2 anchor points I taught you the other day that are guaranteed to be on that graph. What are they? Can you tell me what they are? 0, 1. Okay, good. 0, 1. What else? 1, base. 1, 2, 3. And the base here is 3, right? So I have this graph right here. All right. And then I also have my horizontal asymptote. Now, I'm trying to figure out the inverse, right? I can't get it algebraically yet, but could I look at its graph? And the answer is yes, because we know all we did, how do I get from the regular function to the inverse? What did I do? We flipped the x and the y, right? So instead of this point, by the way, check this out. This is the point 1, 3, which in this case was 1, base. So now if I took the inverse of those, what would the graph look like? What points are guaranteed to be on there? Instead of 1, 0, what would it be, you guys?
0, 1.
Oh, wait. Ah, this is backwards. Thank you. This should be 0, 1, right? And the other one should be 1, 0. Very good. So this one over here. Was that backwards or no? I can't remember. Okay. And then instead of 1, 3, what would it be? 3, 1. So 1, 2, 3, 1. Good. And instead of having a horizontal asymptote, if I'd imagine this being reflected over the line y equals x here, I would get a vertical asymptote here. Okay? So right here, doesn't that look exactly like what we did before with our inverse function, a reflection over the line y equals x? So the question then is, this is the point 3, 1. So the question then is, what is the equation for that graph? That's what we're looking for. If we could get it, that's what we'd be able to graph. So we kind of know what the graph looks like already, but we don't know how to get it, okay? This is the day that you need logarithms, all right? Today is the day that you get yourself out of the problem of solving this little equation for y. We're going to come back, and we are going to solve that for y. So leave a little space right here, okay? So here comes a formal definition for us for a logarithm. Here's our third idea. So our formal definition says this: x is equal to a to the y. This is the symbol for if and only if, meaning it can go back and forth, if and only if, right? X equals a to the y if and only if y is equal to log base a of x. Okay? So I do want to point out a few key things for you. Here's one of them, okay? This whole piece thing, this over here, this is called an exponential equation. Do you guys agree with that? Okay. This one over here, this is called a logarithmic equation, or a log equation. So it is possible to transfer from one to the other using the definition, all right? In this case, over here in the exponential, what does the A stand for? The A stands for, starts with a B. The base, very good, all right? And the Y stands for the what? The exponent. Good. So check this out. The Y, this part, this is my exponent, right? And it's equal to log base A of x. This is still your base. So your bases stay the same. Now there's this relationship that I use to transfer back and forth, and it looks like this. So what I do is I start with my base. I say my base raised to the power of y has to give me x. So I say a to the power of y gives me x. So y is equal to log base a of x. The way that we say all of these things, we say y equals log base a of x. So you want to say what base and then of. So that's how we say that. So if I said this, y equals, how do you say that in English, looking at that? Y equals, how do we say it? Log base 7 of x. Good. How do I say this one right here? How do I say that one? Y equals log base 3 of 9. Okay, good. So now we know how to say these things. So this is our formal definition of what a logarithm is. So let's go right back up here, and I have x equals 3 to the y. How do I solve this for y? Well, the base is 3, right? So we're going to say 3 to the x gives me y, right? So y equals log base 3 of x, and this is the graph for y equals log base 3 of x. Okay, so everyone always asks, what is a logarithm? The answer is, the logarithm is the inverse to an exponential equation. So when you're walking down the hallway and I see you, I'm going to say, hey, what's a logarithm? And you're going to say, what to me back? It's an inverse to an exponential equation. That's exactly right. You guys got it. Okay, let's start exploring these a little bit more. Let's evaluate this log together. Let's explore its meaning. First of all, can I have someone read that expression to me that's on the board right there? What does it say? How do we read that in English? How do we say it? Yeah, Karen. Not power of 32. Log base 2 of 32. So this is log base 2 of 32. All right. So this whole expression here, this has a value, okay? And we're trying to figure out what that value is, okay? So here is what we're going to do in our heads, okay? We're going to tell ourselves, all right, the base is 2. So I got to say 2 to the what power would give me back a 32. So I like to use x for my variable, so I'm going to say 2 to the what power would give me back a 32. Notice that this is a log equation, okay, and I have transformed it into an exponential equation using the definition of a logarithm. So 2 to the what power gives me back 32. Anybody know what that is? 5. Yeah, x must be equal to 5. Okay, so that means that log base 2 of 32 is equal to 5 because 2 to the 5th gives me back 32. Does that sound good? Okay, let's try another one. Here's another example for you. What would log base 3 of 1 be? Log base 3 of 1. Yeah, Bobby, what do you think? He says it's 0. Okay, this has to equal something, right? So we say 3 to the what power would give me back a 1. 3 to the what power would give me back a 1. Well, the only thing that's going to be true is 0. So log base 3 of 1 is 0. Hey, what would log base 5 of 1 be? Bobby says 0 again. Is that true? That's true. Okay. What would log base 11 of 1 be? 0. What would log base 35 of 1 be? 0. Huh. What do you think log base A of 1 is going to be? Yeah, okay, so we kind of figured that one out. That's one of the properties. We'll get to that later. Yes, sir? Okay, log base 4 of 2. Now, next example. Okay, remember, this is an exponent. The entire thing represents an exponent. So the way we figure it out, we say, okay, 4 to what power gives me back a 2? How many of you remember the most amazing fact ever? It says if a to the x equals a to the y, then what? And then x equal to y. Good. This is what we call the most amazing fact ever. I'm sure it has a different name somewhere else, but that's what we're calling it. Okay. So, is there any way I can make my 4 be a base of a 2? So 2 to the 2, right? And this is all still raised to the power of x equals 2. What do I do when I raise the power to a power? So 2 to the 2x equals 2 to the first. Very good. Are my bases the same? So 2x equals 1. X equals 1/2. Okay, so it must be true then that log base 4 of 2 has a value of 1/2. Is this true? This is totally true. Check it out. 4 to the 1/2 power gives me back a 2. 4 to the 1/2 power gives me back a 2. Because 4 to the 1/2 is the square root of 4, of course. And that makes total sense. Okay, I'd like you guys to try this one. Log base 10 of 1 over 100. Talk about this one in your group. See if you can come up with a value for this. Remember, this whole thing represents an exponent. So I would say, yeah, 10 to the what power gives me back 1 over 100. So 10 to the x equals, how about 100 to the negative 1, right? Is that the same thing as 1 over 100? Yeah. So 10 to the x equals, how about 10 squared to the negative 1? So 10 to the x equals 10 to the negative 2. Hey, check it out. There it is. X has to be negative 2. All right. So that means that log base 10 of 1 over 100 is equal to negative 2. We have 4 basic properties of logarithms that we can take advantage of. And we already found one of them earlier. So here we go. The first one is log base A of 1 gives me back a 0. Right? Because, you guys know that B/C means because? You guys know that? Okay. Because A to the 0 gives me back 1. No problem there, right? What about log base A of A? What would that have to be? What if my bases are the same? Log base A of A. What do you think? A to the what power would give you right back an A? 1. Very good. Because a to the first power gives me back a. Now, number 3, there's 2 parts. It says this, log base a of a to the exponent of x is equal to nothing more than x. Because we can say that a to the x gives me back a to the x. Now, there's another way we could write this. Okay, we can also say this. We can also say a to the exponent of log base a of x. That would also give me back x. So part 3 has 2 different properties here. This whole entire piece up here is in the exponent. So a to the exponent of log base a of x would just give you back x. Fourth and final property for us for logarithms is the MAFE, except in log form. So if the log base a of x is equal to the log base a of y, then it must be true that what? X is equal to y. All right, so we'll do this right next to each other. So what would log base 4 of 1 have to be? Yep, that would definitely have to be 0, right? Log base 4 of 1 is 0. What about log base root 7 of root 7? What would that have to give me back? Yeah, that would just give me 1. What about 8 to the log base 8 of 14? My bases are the same. So if my bases are the same, I can say that this just equals 14. You got it. And then if I have log base 3 of x equals log base 3 of 12, are my bases the same? So therefore, x must be what? There you go. X must be equal to 12 in this case. All right. Here's the bonus box for you. You're going to need your calculators for this one. Check this out. If I asked you for, let's see here, 2 to the what power would give me back 11? Okay. What's that? This is a bonus box. Yeah, this is good. Okay, so 2 to the what gives me back 11. So think about this, yes? Okay, look here. We know 2 to the first is how much? 2, good. What's 2 squared? 4, good. What's 2 to the third? 8, good. What's 2 to the fourth? Okay, 16. Okay, so very good, Bobby. So our answer, 11, is in between here, right? 11 is in between 8 and 16. So that means that our answer for 2 to the what equals 11 has to be between what 2 numbers? Has to be between 3 and 4. Do you think it's closer to 3 or closer to 4? 3. I think it's closer to 3. Okay, right now I want you to guess what x you think it was going to be. You can round to like 2 or 3 decimal places. What do you think it's going to be? I'm going to guess like 3.2178. That's my guess. I don't know. I'm taking a guess, right? The answer has to be somewhere between 3 and 4. All right, well, it turns out when you take your calculators out, all right, and it should, when you turn it on here, okay, clear stuff out. When you push the log button, which is over here on the left-hand side, when you push the log button, notice that there is something missing from my screen. What is missing from my screen, guys? The base. Very good. There's no base on my screen. That's because mini calculators, when you push the log function, it automatically assumes you're working at a base 10. That's why when I ask the calculator for log of 100, oh, it's right here, sorry, the log button. Okay. When I ask the calculator for log base 10 of 100, it's going to give me back 2 because 10 squared gives me back 100. So far, so good, right? So then if I know that, what would log of 1,000 be?
3.
It'd be 3 because 10 cubed gives me back 1,000. Now, this doesn't help us because we don't have a base of 10. What do we have? We have a base of 2, okay? So what we need to do then is we need to learn about the change of base formula, all right? So a little bonus box says this. If you have log base a of b, it's the same thing as taking log base 10 of b divided by log base 10 of a. So all you have to do is divide them. And I drew a little slash right there to remind myself to divide them. Bigger number on top, smaller number on the bottom. Okay. So how do I figure out what this one's going to be then? Well, I want 2 to the x equals 11. Let's change that to log form. What would that be? Log base 2 of 11 equals x, right? So I'm going to plug this into my calculator using the change of base formula. All right, so here we go. Follow along with me. I got log 11 divided by log 2. All right, now my guess was about 3.2178. Let's see what I got here. I was a little bit off. It's 3.459. Is that a reasonable answer for us? Yeah, it's closer to 3 than it is to 4, kind of in the middle there, right? And so that means that, check this out, if I go 2 to the power of 3.459, I should get what back when I push enter? I should get close to 11, and check it out, I get 10.9967 and then some change. All right?